All right, let's get this party started so I can go home and cook dinner. My name is HillaryGreen-Lerman. I am a data scientist at Newton, and my special job is to prove whether or not things work. So I'm going to start with a little bit of an introduction to how I think about data science, emphasis on the science part. My background is doing actually pharmaceutical research. So yeah, I think that at the core of science is doubt. And I want to tell you a little bit about how I go about doubting my data. So for instance, we've all heard that 4 out of 5 dentists recommend Trident. But what does that really mean? You know, 4 out of 5 dentists might also recommend killing Cecil the lion. So maybe dentists just have really poor judgment and Trident's not such a good idea. This is a little bit more serious example. I was listening to NPR a few months back, and they had a great story about female veterans returning from Iraq and Afghanistan, and they said, you know, oh my goodness, female veterans are twice as likely to be unemployed as the general population. And that is terrible, regardless. But it would be interesting to know what the unemployment rate is for male veterans. It might be the same. It might be that female veterans are actually doing slightly better. We don't know. That's why we have to always be questioning our data and asking about a control, about something to compare it to that gives us context. So in traditional science, we have a really good way of doing this. It's called a randomized controlled trial. We take all of our subjects who, you know, we've convinced and made sign waivers and said they want to be part of our trial. We do something to establish a baseline. That could be comparing everyone's demographic information. It could be taking everyone's blood pressure. It could be giving all of your students a pretest. Then we randomly split into a control group where nothing happens and a treatment group where we do something that we're interested in finding out its effect. Let that happen for a while, and then we measure all of the outcomes, preferably something that is similar to the baseline that we established initially. And hopefully, we get a graph that looks like this. In particular, hopefully, we have a nice variance so we can get some idea of whether or not our result was a happy accident or really something that's statistically significant. The problem with big data and data science is we generally can't conduct these kinds of studies. We're stuck with something called an observational study. And that means that we already have the big pool, we already have the baseline measurements and the final measurements, but we didn't get to control how the randomization happened. And we didn't get to control maybe exactly how the treatment was administered. So a couple problems. So one, oftentimes our groups are self-selected and there's probably some bias. You know, why did they click that link? Why did they, you know, choose to use that product? There's probably some good reasons behind that. And we're not allowed to just, in a lot of cases, to deny treatment and do A/B testing. If somebody is paying for a product, they're going to be pretty upset if they don't get that product or if they get some sort of placebo product. So yeah, so with these limitations, how can we have good controls in studies of big data? So I'm going to take a break for a little moment and tell you about where I work, about Newton. Newton provides personalized digital courses for global publishers. And the sort of bottom line is rather than having every student work on the same thing, we provide a way for publishers to give differentiated instruction. And that means that students get help with what they're struggling with and not with things that they're not struggling with. And they're able to demonstrate proficiency, move on, and do other things. And I have a little demonstration of this. This is my baby right now. This was my Learn JavaScript project. Used a lot of Python to get the hang of, to get all of the data and find what I wanted to use, and then JavaScript to code it up. So you, of course, can't see what's up here because the resolution is a little bit unhappy. But basically, this is how we represent how different concepts are related to each other. So the gray so these are all related to some elementary students learning multiplication. The gray concepts are prerequisite things like understanding multiplication, multiplying whole numbers within 100, multiplying whole numbers and something that I can't read because of the resolution. And then the colored things are the goals that their teacher has actually assigned for them to get. They need to interpret multiplication equations, multiply by one-digit numbers, multiply by two-digit numbers, and solve multiplication word problems. These are all 3 real students, real data, just pulled out. And let's talk a little bit about what happens. So the first 3 questions are the same for everyone. This is because it's their very first day using Newton, and we don't know a lot about them. But you see that right at this point, by the way, sorry, each of these boxes represent a question. The color represents what the topic was, which of the concepts in the knowledge graph they were asked about. So they were asked about gray, then yellow, then blue. Notice that our middle student has missed a question on blue. They've got that little red X, which means they got it wrong. And now we're going to see differentiation kick in. So while the other 2 students move on to green, our middle student is going to get another question on blue to try and figure out, was this a fluke or is he really struggling here? Notice also that the student over here has missed a question on green, so you're going to see the same thing happen. And if we let this go for a while, you'll see that the middle student is going to stay on blue, the far right student is going to stay on green, but eventually they'll learn stuff. They go all to the green checks, and we let them move on. So notice also that our strong student has been able to finish and go on and do other things like maybe talk to their teacher, get some enrichment activities, start on the next assignment. And so, yeah, this is what Newton is. This is how it's working. So, yeah, I'll go back to present. So yeah, so my job is to figure out, this all looks great in theory, but is it actually helping? I just, let's be honest, I just cherry-picked those 3 examples that looked really, really nice. What's happening overall if we look at all of our data? Conveniently, one of our many products has this really nice workflow. Every teacher gets to assign whatever they want as a non-adaptive assignment. That's going to be our assignment 1. If students score below a certain threshold, they get a Newton-powered follow-up assignment and then go on to work on assignment 2 at a later date. But if students scored above a threshold, then they go straight to assignment 2 and don't have Newton. So this is great. We've got a treatment group and a control group, and it's got all these problems associated with observational studies, but it gives us a place to start. So there are a lot of ways that we could, so let's take a step back, though, and look at the breakdown of the data that we get from this product. There's lots and lots of students using it. And some teachers, you're not required to have that adaptive follow-up. It's a little button that the teacher can flick on or flick off, and some teachers just don't flick it on, and their students never see adaptivity. Some students do flick that button on, and some percentage of their students see adaptivity. So we get this sort of hierarchy. And it's really only these teal students at the very bottom who actually are getting the adaptive follow-ups. There's a couple ways we could analyze these data. We could compare the whole classes who don't use adaptivity to the whole classes that use adaptivity. There's a couple issues here. One is we don't know why they chose adaptivity or non-adaptivity. But the other problem is that there's a lot of uncontrolled variables in terms of the classes. Classes are learning the material in different orders. Some classes have better teachers. Some classes have worse teachers. We don't know, it could be that all the teachers who aren't using adaptivity are at community colleges, and all the teachers who use adaptivity are at four-year universities. That would be a huge uncontrolled variable. Nevertheless, we did actually do this study, and we saw a statistically significant Newton effect, so yay. But we wanted to look at some other things too. So instead, we decided to compare students within the same class. They have the same teacher, the same TA, the same assignments, the same order of subjects, and see how Newton was affecting them. So you can imagine this is all, and I'm being very careful in marking all of my pseudo data as pseudo data. Anything that doesn't have that little gray thing is actual data that I've pulled. You can imagine we have a class. There's an assignment 1 and assignment 2. This is my little grade book. Some people did an adaptive follow-up. Some people got no treatment. And what we're going to do is, rather than look at just their grades on assignment 2 and use that as our metric of choice, like we know that the students who are getting the adaptive follow-ups are getting them because they're struggling. So we don't necessarily expect they're going to do better on assignment 2 than the non-struggling students. So instead, we're going to look at their improvement, how they did from assignment 1 to assignment 2. We'll take the averages and we'll take the difference. And we'll call the difference in improvement between the two groups the differential improvement, which makes sense. One of the really nice things about this quantity is, assignments differ in difficulty. This is a science textbook, so you can imagine that your first lesson in physics, you're learning about vectors, it's pretty easy, and then all of a sudden they've got you doing Newton's laws, and you're like, I have no idea what's going on. Anyway, you can have everybody have negative improvements, so basically, assignment 2 was just harder than assignment 1, but you can still compare the two groups and still get a positive differential improvement, which would mean that the adaptive group is still getting more benefit. Okay, so we take these grade books from all pairs of assignment 1, assignment 2, assignment 2, assignment 3, and all the classes that we find, and we average the whole thing up, and we get a nice histogram of differential improvement. The dotted line here represents 0, so that would be no difference, and the black line represents the mean. And so you can see we're at like 12 percentage points differential improvement, which is amazing. In fact, it might be too good to be true. If we think about, so this is looking at everybody's score on assignment 1 that we used in the study and just smushing it all together. As we expect, the adaptive students are going to have lower assignment 1 scores than the no treatment group. That's what we expected, right? Because there's a cutoff for whether or not you get offered the follow-up. And in particular, if we think about it, all these students here at the very end, they can't improve on their next assignment. They can't go past 100%. Similarly, all the students at the low end, they've got all this room to improve, and they can't do worse because they can't go below 0. So this is introducing some sort of bias. There's also the bias that, like, if you get a bad grade on a test or a quiz or whatever, you're more likely to go and get help from your teacher. So this is what we're dealing with. So what we thought was, let's build a control group. Wouldn't it be great if we could find some students that have these same distributions of grades, but nobody got any treatment, and see what kind of difference we would expect between those two groups? And then we sort of, if we did better than that with Newton, then we know that Newton was actually doing something beyond just the inherent difference between the populations. All right, so how do we do that? We're going to go back to these classes with absolutely no adaptivity, and build our control group. And once we build our control group and do those same calculations again, the difference of improvements, we're going to call that our constructed baseline differential improvement, or CBDI, which I will use going forward. I apologize for it being a very long and unhappy name. Okay, so here's what we're going to do. We're going to take the grade, the students from those totally non-adaptive classes, and we're going to subsample and split out and create a lower scoring group and a higher scoring group whose scores mirror the distributions that we're trying to match, the distributions from the actual classes with adaptivity. How do we do that? We're going to randomly select a student from the non-adaptive class with replacement. We will check the probability that this student should be included in the subsample, and I'll tell you in a moment how we get that probability. We get a random number. If the probability is greater than the random number, we include the student in our new sample, and then we just repeat until we get our desired sample size. Okay, so how do we actually figure out who to include? Well, we do it by grade. So for instance, if we're looking here at Bob with the 80%, we say, okay, how frequently did 80%, a score of 80% occur in the no treatment group from our original differential improvement calculations? But then we have to divide by how often that 80% occurs in the class that we're sampling from. And so in that way, we're going to end up emulating our original distributions. So this is sort of a visual example of what we're doing. We're basically dividing one histogram by another to get a new histogram. And the way that the subsampling works is, say we do our random draw, we draw Debbie. Debbie has a 65. We look over here and say, a 65 has about an 11% chance of being chosen. We do our random number thing, and Debbie gets included or not included. And we do this until we build up our brand new grade books that we can use. Notice that in these grade books, we are allowed to repeat a student within the same grade book. So Debbie shows up twice in the pseudo-adaptive group. We're also allowed to have students show up in both groups. So Cindy shows up in both the pseudo-adaptive and the pseudo-no treatment group. Totally okay. Another thing that's important is when you do this subsampling, you have to do it a bunch of times independently. because there's actually a lot of variance. And it turns out that statistically that variance actually has a meaning, and you can use it to do statistical things, which I won't go into now. The important thing is, for this experiment, we played around, and it turned out that n equals 50 was a good number of draws for us to do. And then we did this thing. This is called a QQ plot. Anyone know what a QQ plot is? Woo! You want to tell us?
Yeah, it checks for, I guess, if your data is normally distributed, right?
So yeah, you can compare to a norm. Yeah, it compares distributions. So what you do is you say, you have two data sets. You say, what's the 10th percentile of one data set? What's the 10th percentile of the other data set? Drop a point there. What's the 20th percentile, 20th percentile? Drop a point there. And you can see there's a little bit of skew at the very, very low ends. It's not very much if you count each of these is 1 percentile. So you see, like, by 5 percentile, it goes away. And that has to do with when you're sampling, if you just don't have any draws from a certain range, it's hard to draw and make things match up. But cool, we're basically matching what we did for the math was correct. And what's even cooler, so again, these are the plots. The dotted line is at 0. That would be no difference. The solid line is at the actual mean. So that was our original differential improvement, the 12 percentage points that we said, holy something, that's way too much. And then this is what we get if we look at our constructed baseline differential. So drawing out the students and saying, what would happen if I started with these two distributions, but I didn't do anything? Yeah?
So here the control was no extra work versus Newton's adaptive extra work. Is there a comparison between Newton's adaptive extra work and non-adaptive extra work?
I would so love to do that study. Unfortunately, that falls into that category of if people have signed up and paid for Newton, they're going to be kind of upset if we just give them some random extra work. We are working a little bit, so going forward, some of our new partners are interested in doing that type of study and willing to, they're paying for Newton, but they're also willing to do this kind of comparative study. So hopefully we'll look at that a little bit. I mentioned that there was another study way up here. Yeah, this study. So this study, they compared question by question. So like for question 15 on page 70, how did people do in both classes? The wonderful person, Ilya Bomash, who did that study, controlled for the amount of work people had done prior to that question. And he actually saw that it didn't matter how much work they'd done, the adaptive still did better. But you're right that that is one thing that is not controlled in the study, and I would love to be able to do an actual randomized control trial where I could do that kind of a study. Sorry, can you say that? It wasn't a propensity score matching. It was literally just the subsampling that we were doing. The propensity score matching, you needed more data than we had. So this was still just basically trying to build these big class sets and then just compare the two. Yeah. Yes?
What do you think, so this is kind of aside from statistics, I think it's kind of unique that Newton's actually rigorously testing your product, like a pharmaceutical company would. Like, I work in finance, so we have to do this because if it doesn't work, we lose money, right? So there's a very natural thing that's forcing us to test our own assumptions. But in other companies where data science is done, unfortunately, what often happens is if you're selling a product, if you do bad data science, nobody has access to your data, so no one's going to check you, right? Like, so what do you think it is about Newton or about sort of building a startup or a company, whether it's Newton or a marketing analytics firm, that creates a culture of like actually checking your assumptions all the time?
So I think education has a big part to play in it, and that people are much more worried about what happens to their children than they are about, whether or not your ad tech solution is the best. And there is a lot of pressure, but it's still astounding how much basically bad science is done. You can read, there's a site called EdSurge, and they had a whole big series of articles on efficacy and how people were trying to do efficacy. And there were some really cool examples, but there were also a lot of people who just said, You know, we took a class of kids, we gave them a quiz at the beginning, we let them play with our product, we gave them the quiz at the end after, you know, a week where their teacher could still be teaching them, they could still be going home and doing other homework. And what do you know? They were better at the end than they were at the beginning. Our product works. So there's still a lot of work to go. But I think that education has a big part to play in it, and I think, you know, being a startup that's trying to, you know, really prove yourself to people, and, you know, people are very, very rightly saying, show me, show me, show me, that definitely contributes to the culture. And, you know, I'd like to think also that Newton is just, you know, a bunch of really nice people who care. Any other questions? Cool, I think we did exactly what we were supposed to do in terms of time, right? Yeah. Awesome sauce.